Assalamualaikum and good day to Dr. Mariam. My name is KRISHAN ARPIDANI bin Muhammad Daniel Philip. My matrix number is 207300 and I will be presenting on FM modulation and demodulation using PSA software. So today we will explore the frequency spectrum, power total, occupied bandwidth, and the process of demodulation for different modulation indices, which is M. Right. So before we begin, we would like to discuss what is frequency spectrum. So let's briefly review the basics of FM modulation. So frequency modulation is a method of encoding information onto a carrier wave by varying its frequency according to the modulating signal. The modulating signal can be an audio signal, for example, speech or music. So as you can see from the graph above, the modulating signal varies the carrier frequency, resulting in sidebands around the carrier frequency. The number and spacing of these sidebands depend on the modulation index. So carry on. All right. So now when the modulation index, which is M, is equals to 1, the frequency deviation is equal to the maximum frequency of the modulating signal. In this case, the frequency spectrum consists of a central carrier frequency and four sidebands. The sidebands are symmetrical and equidistant from the carrier frequency. The bandwidth of each sideband extends to the maximum frequency deviation. So, based on the graph for the frequency spectrum at modulation index 1, the highest frequency is at 1 megahertz, where the power is 7.34 dBm, whereas the lowest frequency is at 919.84 kilohertz, where the power is negative 42.856 dBm. Now, let's consider the case when the modulation index, which is M, is equals to 2. So when the higher modulation index, the frequency deviation is doubled. As a result, the frequency spectrum consists of a central carrier frequency and 5 sidebands. However, the sidebands now extend up to twice the maximum frequency deviation while the carrier frequency decreases in power. So based on the graph above, for the frequency spectrum for modulation index 2, the highest frequency is at 1 megahertz, whereas the power is negative 3.337, which was lesser than the previous modulation index, which is 1. Whereas the lowest frequency is at 899.69 kilohertz, where the power is negative 33.45 dBm. All right. Moving on to the modulation index of 2.5, we can observe a similar pattern. The frequency spectrum still contains a central carrier frequency while having an additional one sideband, which in total equals to 6 sidebands. However, the sidebands now extend up to 2.5 times the maximum frequency deviation. So now we can see at the central frequency, the highest frequency is at 1 megahertz, where the power is negative 16.64 dBm, whereas the lowest frequency is at 880.23 kilohertz, which is located at the last sideband, and the power is negative 38.199 dBm. All right, now let's discuss the power total for different modulation indices. So power total refers to the total power contained in the FM signal, including the carrier and sidebands. So for M1, the power total remains constant regardless the modulation index. It is only affected by the power of the modulating signal. So based on the graph, the power total for modulation index 1 is equals to 9.668 dBm. So now for M2 and M2.5, the modulation index 2 and 2.5, the power total decreases a little proportionally with the modulation index. As the modulation index increases, more power will be distributed to the sidebands. So for the power total for modulation index 2, the power total is 9.65 dBm, whereas for modulation index 2.5, the power total is 9.648 dBm. So we can see there are not so much differences, but there is a slight decrease when the modulation index increase. Now, moving on to the occupied bandwidth, OBW. So OBW refers to the range of frequency required to transmit an FM signal. So now for modulation index 1, the occupied bandwidth is determined by the maximum frequency deviation. So for modulation index 1, the OCB is equals to 83.05 kilohertz. Whereas for modulation index 2 and modulation index 2.5, the occupied bandwidth increases linearly with the modulation index. So the wider the modulation index, the broader the range of frequency needed to transmit the FM signal. So for modulation index 2, the OCB is 125.52 kilohertz, whereas for modulation index 2.5, the OCB is 152.9 kilohertz. So we can see a pattern where if we increase the modulation index from 1 to 2.5, the OCB will increase from 83.05 kilohertz to 152.9 kilohertz. Finally, let's discuss the demodulation process for FM signals. So demodulation is the process of extracting the original modulating signal from the FM waveform. So in traditional FM demodulation, we use a frequency discriminator or a phase lock loop, which is PLL, to recover the modulating signal. These techniques rely on detecting and measuring the changes in the carrier frequency caused by the variations in the modulating signal. Now, in conclusion, um, FM modulation and demodulation are essential techniques for transmitting and recovering information in the systems. The frequency spectrum, power total, and occupied bandwidth vary with the modulation indexes, allowing us to obtain the information that we needed if we increase or decrease the modulation index. So that is all from me. I would like to say thank you, and I hope you guys have learned enough from my presentation. Thank you.